Okay, so in this section, we're going to talk about how to determine the multiplicity at each x-intercept or at each zero to see if we can get an idea of what the graph would look like. So let's take a look at suppose we're given something like this. Y is equal to x squared minus x minus 42. And you wanted to know, where are the zeros? Well, the first thing I would do is I would look at the 42, and I would come up with all of the numbers that multiply together to give you 42, but have a difference of 1. And this is just factoring. We did factoring in integrated 2, and we'll review it in integrated 3. So let's take a look at the numbers that multiply together to give me 42, but have a difference of 1. Well, I could use 1 and 42, except I can't get a 1 with a 1 and a 42. A 2 and a 21 won't work either. And I could keep going through, but I'm going to cut to the chase here, and I'm going to say 6 and 7 are my best options because 6 times 7 will give me 42, and they have a difference of 1. And since this sign here is negative, that tells me that the signs have to be different, and the biggest number is going to take the negative value, which means the 7 has to take the negative value, and the 6 takes the positive value. And the rest of it is just going to be x and x. Now let's make sure we factored this correctly. So if I FOIL this, the first terms multiplied together will give me x squared. Outside gives me negative 6x plus, negative 7x plus 6x is minus 1x, which is what we have in the problem. And then positive 6 times negative 7 is negative 42. So I know that this is the factored version. And we learned previously that if x plus 6 is a factor, then negative 6 is a 0. Also, if x minus 7 is a factor, then positive 7 has to be a 0. And if you look over here on the left, this is the factored version. And again, notice that when x is equal to negative 6, say here, we have a 0. And then when x is equal to positive 7, say here, we have a 0. And we said that the reason we factor, right, is so we can find those zeros. Notice that y is equal to 0 for both of those red points. Those points are on the x-axis. But today we're going to talk about multiplicity. If you look at the factored form, if you look outside of parentheses, technically there's a power of 1 here and here. And since you have a power of 1, that's an odd multiplicity for each of those zeros. If you have an odd multiplicity, it means that it touches that 0 and slices all the way through. So notice that when x is negative 6, since it has a multiplicity of 1, that means it slices through, all the way through the graph at that 0. Also at 7, we have an odd multiplicity because we have a 1 there. And notice that through the graph, it slices through as well. But look to the right, look at this one here. It's true that negative 6 is a 0, and I'll graph it here. That's the point negative 6, 0. And also positive 7 for this factor is a 0. And I'll just say it's right there. And if you look at the multiplicity, the negative 6 has a multiplicity of 1, and the positive 7 has a multiplicity of 2, which is even. Remember, we said that if the multiplicity is odd, then it slices through at that point. Well, notice that the graph just slices right through there. It passes through the x-axis. But since x has a multiplicity of 2, it does a bounce. In other words, the graph will come down, it will hit that 0, and since it has an even multiplicity, instead of slicing through the graph, it bounces back up. So if it's an even multiplicity, you have a bounce. If it's an odd multiplicity, you have a slice. Let's take a look at the bottom left, this graph and this polynomial function here. Notice that -6 is a 0, and we'll graph it here. We'll mark it here. And notice that +7 is still a 0, and we'll mark it there. But since this time the -6 has an even multiplicity, that means that at that 0 we have a bounce. In other words, the graph will come up and bounce, right? And then go back down. If you look at +7, notice it has an odd multiplicity of 1, so at 7, it slices through the graph. And finally, if we look at the function here, notice that -6 is a 0, and we'll graph that. And notice that +7 is a 0, we'll graph that. On both of those, we have even multiplicities. We have a 2 here and a 2 here. That means we have 2 bounces. So notice that when x is -6, we have a bounce. And then when x is +7, we have a bounce. Let's take a look at a couple of more situations. Suppose I factor and I get something like this. Okay, in this situation, I have 2 zeros. I have a 0 when x is 1 and when x is equal to -1. So if I wanted to sketch this, I know that at the point where x is 1, I would have 1 minus 1, which is 0. So I know that 1 is a 0. And I know that if x is -1 here, -1 plus 1 would give me 0. So -1 is also a 0. And what's the general shape of this graph? Well, since I have x to the power of 2 here, technically on the left, and x to the power of 1, this is an x to the power of 3 if I were to multiply all of this out. So this is going to be an odd function, and since it has a positive in the front, it's going to be an odd positive function, which means it has to start low, referring back to the tails. It starts low and it ends high. And I know that at -1, I know that it has an odd multiplicity, which means it has to slice through that graph at -1. So it's going to go up and slice through. And then I know that when x is equal to +1, it has an even multiplicity, which means we would have a bounce. So the graph would look something like this. We would have a bounce. Now, just to get a little extra information, if x is 0, then I would have a -1 to the power of 2. Well, -1 times -1 is 1. And then over here, I would have a 1. So 1 times 1 is 1. So if x is 0, I know that y is 1. So there's another point on the graph that we could derive. And just as sort of a review, we know that we have a 0 at -1. We have a 0 at +1. We have a y-intercept value of 0, 1. And again, just by looking at the graph, we can tell that this is an odd graph because the tails go in opposite directions. And since it starts low and increases over time, we know that it's a positive graph. What about a graph that looks like this? Would this be odd or even? Well, to determine that, look at the tails. Do the tails go in the same direction? Well, in this case, both tails point downward. So this would be an even function that happens to be negative because the tails are pointing down. So this is even and negative. And let's do a quick search here. I'm going to show you this because we have a wealth of information available to us online. And I'm just going to type in multiplicity of a function. And as you can see, a lot of examples pop up here. I'm going to look at images, and I'm just going to pick a few out and we'll talk about these. Let's look at this one here. I hate to have so many different options to look at, but let's focus on this graph on the right. If we look at the function here, notice that the tails point in the same direction, right? They're both pointing up. So would this be an odd function or an even function? Well, since both are pointing upward, that makes it an even function. I will try to write even here. So we have an even function. And since they're both pointing upward, it's a positive function as well. Even and positive. And notice that, let's see, how many directions does this thing take here? It goes down. That's 1, 2, 3, 4. So this could be a fourth degree, a positive fourth degree. So it might, let's see if we can determine some other things here. I can tell that -3 is a 0. Well, that makes x plus 3 a factor. And since it slices through, it has to have an odd power. It has to have an odd multiplicity, right? So let's see, if -3 is a 0, then we know that x plus 3 is a factor. We'll have that there. And then we know that -1 is a 0, which means x plus 1 has to be a factor. And we know that x is -1. We know that it slices through the graph, so it has to have an odd power there. So we'll just leave a 1 there. But notice that x is equal to 2 is a 0, which makes x minus 2 a factor. And we have a bounce, right? We have a bounce there. In other words, as the graph comes in from the left, it hits x is 2 and bounces back up, which means it has to have an even exponent outside. So it has an even multiplicity. So we'll just do this. We'll just put a 2 there. And I'm going to make the claim that this is very close to the function itself. Very close. Now, if we were calculus students, we would do a lot more to this graph to be a little more accurate. But if we were to type this into Desmos, we would get a graph that looks very much like this one here. Okay, so that pretty much serves as a good review of an odd or an even function and taking a look at the multiplicity. Let's do one more and we'll finish up for the day. Let's look at, say, this picture here. Notice that for this function, we have a 0 at -2, which is going to be this point here. And then we have a 0 when x is +3, which would be this point here. And notice that when x is -2, we have an even multiplicity, which means we would have that bounce there. And they've got the bounce graphed. And then over here where x is +3, we have an odd multiplicity, which means the graph has to slice through at that point. We have a slice there. Notice that this is an odd function because we have a power of 3 here and a power of 2 here, and 3 and 2 adds up to 5. So we have an odd function, we have a negative in the front. So not only is it odd, which means the tails go in opposite directions, right? But it's also a decreasing function, which means it starts high and then it does some things in the middle and it finishes low. Okay, so there there we have it. That's our review of looking at a function, evaluating the multiplicity at the zeros, and then trying to determine the end behavior. Thank you.